Hi, welcome to a new lecture from the course Foundations for Machine Learning. We are learning about linear algebra, and specifically in this lecture, we'll be looking at matrix multiplications. What we are trying to understand in this lecture is the intuition that matrix multiplication is essentially a linear transformation. So we'll see how that happens, how vectors are transformed in a linear fashion when you multiply them with matrices. This is an operation that is commonly seen across machine learning. So if you have a fairly good geometric or intuitive understanding of this whole idea, it makes your foundations very, very strong. So let us start with what do we mean by a transformation? A transformation is nothing but something that changes an input vector to an output vector. So here I have drawn a 2D space xy, and I have a vector v1 and vector v2. And a transformation is defined as, you can think of it as a function f, which transforms the vector v1 into v2. So please note that in this lecture, I'm not strictly following the convention of what should be input vector and what should be output vector, as in I may be using the notation u or v interchangeably for input or output, but wherever I'm using v as the input vector or u as the output vector, I'll be very clearly defining what is input and what is output. So please don't get confused if I'm not sticking with certain notations that you may be familiar with. So a transformation is nothing but something that changes a vector into something else. So here we see that the vector is still in the 2D space after transformation, but it has the head, or its tip rather, it has moved. Now there are several types of transformations, but specifically we are trying to learn about linear transformation, and this is probably the cornerstone of linear algebra. If there is one concept that you should absolutely master in linear algebra, it is definitely linear transformations. Linear transformation has two properties, as I have written here. All straight lines must remain as straight lines. This is the first property in a linear transformation. The second property is that the origin should not move. The origin should remain fixed. Now, let us see what the first point specifically means. When I say origin should not move, I'm pretty sure that you can imagine that really well. But when I say all lines must remain as lines, I'm not really certain that you are imagining the exact same thing that you are supposed to imagine. So what lines are we talking about here? Let's start with an example, right? So let's visualize a particular transformation. Some of these transformations may be linear, some of them may be not linear, but let's see. So here, imagine you have three vectors that are inputs into the transformation, v1, v2, v3. And you have three vectors that are outputs, u1, u2, and u3. My question is this a linear transformation or not? One of the ways to see whether this is a linear transformation or not is to check if the two properties above, all lines must remain lines, origin should not move, whether these two conditions are satisfied or not. Now, you might be wondering that, oh, the vector looks like a straight line, so this is a linear transformation because the lines are remaining as lines. No, that is not what we mean by the lines here, because there are no vectors like this. If you have something like this is not a vector, right? There is no vector that looks like this. So obviously, all the vectors are going to look like straight lines only. So we are not talking about that straight line. So what are we actually talking about? We are talking about the line formed by the tips of vectors. So imagine that these three vectors are 3 points that represent the coordinates of the tips of the vector. So when I say tip, I mean the head of the vector, and tail is this. So tail is the back end of the vector, tip is the head end of the vector. So here these 3 points are essentially on a straight line, right? Now you can imagine that v1, v2, v3 have 3 corresponding coordinates which correspond to the head of these vectors. Now let's see what happens to those coordinates after transformation. So after transformation, v1 becomes u1. So now the new tip is this. v2 becomes u2. So the new tip is this. V3 becomes U3. So the new tip is this. And you can see that the modified tips are also on a straight line. So this straight line got transformed into this straight line. So the lines are staying as lines. And on top of that, the origin has not moved. The transformed vectors as well as the input vectors have the same origin, which is 0, 0 on the coordinate system. So in this case 1, we can see that this is essentially a linear transformation. Now let's look at another case, case 2. In case 2, we have again the same 3 input vectors. So we can define the 3 coordinate points which form the tip of these vectors, right? So these 3 points, we can see that they are on a straight line. But now let's look at the transformed vectors, u1, u2, and u3. So the u1 has tip here, u2 has a tip here, and u3 has a tip here. So we can see that the points that form the head of these 3 vectors after transformation, they do not lie on a straight line. So the straight line over here got transformed into something that is not a straight line, because we cannot draw a line between this point, like, this point, and this point do not lie on a straight line. But the origin is still, intact. The input vectors have 0, 0 as the origin, and outputs also have 0, 0 as the origin. So here in the linear transformation, among the 2 conditions, the second condition was satisfied in this case 2. But the first condition, all lines must remain lines, it was not satisfied. So this is not a linear transformation example in case 2. Case 1, this was a linear transformation, but case 2, this is not a linear transformation. Let us look at one more case. Here you have 3 vectors, v1, v2, v3, and imagine they are transformed into u1, u2, u3. Is this a linear transformation? The tips are in a straight line over here. So these tips of input vectors were in a straight line. The tips of the output vectors are also in a straight line. However, this is not a linear transformation because the tail of these vectors are now no more at the origin. So the origin has sort of shifted from 0, 0 to something else. So in case 3, this is also not a linear transformation. But case 1 was a linear transformation because the straight lines remained as a straight line. The origin was unaffected by the transformation. So this is how we should visualize linear transformation. So always visualize where the tips of the vectors are moving whenever a transformation is happening. And by tracking those tips, we can track whether straight lines remain as straight lines or not. So now let us see how to numerically describe some of these transformations, because so far we have been describing it a bit qualitatively. So take an example of a vector, let's say vector v in xy plane like this. V is described in this specific example as I plus 2j, because on the x-axis the dimension is 1, along the y-axis it is 2. So the vector v is defined as 1i plus 2j, and you should remember what this is. This is scaling plus linear combination of the 2 basis vectors. I and j are the basis vectors here, right? And you can express any vector in the xy coordinate system using these basis vectors. And I and j are probably the most fundamental basis vectors that any student learns first. And you can represent this vector v in terms of the scaling. So what do we mean by scaling here? We multiply by a scalar. So here the scalar number using which the vector I is multiplied is 1. The scalar number by which vector j is multiplied is 2. And why do we say linear combination? Because we are directly adding those 2 vectors. So v is defined as the scaling plus linear combination of I and j are the basis vectors. So this sounds trivial, right? So why am I mentioning this? I'm mentioning this because I also want to show you how this same principle applies after we do the transformation on top of vector v. So let us define a very simple transformation. Let's say the transformation involves 2 steps. First is rotation by 90 degree counterclockwise. So whatever vector is present in the in this transformation, it will be rotated by 90-degree counterclockwise. And also as part of the transformation, the same vector will be simultaneously scaled up by a factor of 2. So the size of the vector doubles, but the vector itself will get rotated by 90-degree. So we can see what happens to this particular vector under such a transformation. So the original vector v, this will be rotated by 90-degree counterclockwise in the counterclockwise direction. So this is 90-degree. But will the vector remain like this? No, right? Because it has to scale up. The scaling factor is 2. So let me duplicate this vector. Something like this. And this. So now this is the transformation of the vector v. So let me write this as transformed v. Which one? This long guy, not this guy. So I'll delete the smaller vector perhaps. Okay. So now this is the transformed v. So you can see the two steps that happened. 90-degree rotation in counterclockwise direction and scaling by a factor of 2. So now what we did right now is we tracked what happened to v. Similarly, can we keep track of what happens to I and j? So we said we have to scale, we have to rotate by 90-degree clockwise and scale counterclockwise and scale by a factor of 2, right? So what will happen to j? J should also be rotated by 90-degree counterclockwise and scaled. So j, the origin will remain here, but it will become this after transformation. I can increase the thickness so that you can see better. So this is the transformed j. Let me write it over here. So this is the transformed j, right? And what will happen to I during this transformation? I can duplicate I. I will be rotated by 90-degree and scale by a factor of 2. I can increase the thickness. So this is the transformed I. Transformed I. This guy. So now let us formally represent the vector v once again in terms of the transformed I and transformed j. But before that, let's just write this down. What happened to I? I just want to erase some of these things so that you are not able to see this. Let me move this out of your sight. I'll come back to you to explain the transformation that is happening to vector v in terms of transformation that happened to vector I and transformation that happened to vector j. So we saw that v is defined by the linear scaling plus linear combination of I and j, right? So v was nothing but 1 times I. So here the scaling factor for I is 1 and 2 times j. Scaling factor for j is 2. And then we are doing a linear combination of these scaled I and j vectors. And what is v prime or transformed v? This transformed v I can also denote as v prime or u also, whatever is convenient for you. So maybe I'll denote it as u. The transformed v I will call as u. So u equal to, just tell me what does u look like? U looks like 2 times transformed j, right? 2 times transformed j. Maybe transformed j I can write as jt. So this is j transformed. Transformed I can denote as it. I'm sure some of these notations are probably used in some other context, but I'm not referring to any of those contexts. I just want to keep it to the geometric intuition at this point. So you can see that the transformed v equal to 2 times transformed j. So that will be this plus 1 times transformed v. Sorry, transformed I. plus 1 times transformed I transformed, right? Now, here is where the things get interesting. So I can write this in the correct order. This is 1 times I transformed plus 2 times J transformed. So this one you saw visually, because visually you can see that this red vector, which is the transformation, is 2 times this guy. I need the yellow vector 2 times, and I need the green vector once, this green vector. And if I add this plus this, I can get the transformed V. So that is how I wrote it as 2 times J transformed plus 1 times I transformed. And then I flip the order. I make it such that this 1 times I transformed is coming in the beginning. Like it's written in the beginning, and 2 times J transformed is written second. Now, what do you see? You can see that the original vector V was 1 times I plus 2 times J. The transformed vector V, which we call as U, is again 1 times transformation of I plus 2 times transformation of J. So that is what I have written here. If V is defined by scaling plus linear combination of I and J, then V1 or V transformed, whatever you call it, V transformed or U, is defined by the same scaling factor. So that's why I have written this word extra, the same scaling plus linear combination of I1 and J1, or rather I transformed IT and J transformed JT. So that is what we saw here visually. We can also prove the same thing numerically very easily, because what happens to I in this case? I has transformed to become the coordinate of the I will, that coordinate of the tip of the I will be 0, 2, right? The X coordinate will be 0, Y coordinate will be 2. So basically this will be the new, this is the position where the I moves to. So I will transform to this guy. What happens to J? J will transform to this guy. J is scaled by a factor of 2 and rotated by 90-degree counterclockwise. So J will have minus 2 as its X coordinate after transformation and 0 as the Y coordinate after transformation. So this I can also write as, in my previous coordinate system, I is essentially becoming 2J, similar to 2J, and J is like becoming minus 2I, right? So I became 2J, and J, which was this vector, it became minus 2I. So I transforming to this, J transforming to this, and what is now the new transformed vector? The new transformed vector will also follow the same thing. 1 times whatever is the transformation of I plus 2 times whatever is the transformation of J. So that is 1 times whatever is the transformation of I. Transformation of I is 2J plus 2 times whatever is the transformation of J. 2 times transformation of J is minus 2I. Minus 2I. So this will be 2J minus 4I. And this can be written in the proper order as minus 4I plus 2J. Is this what the new vector looks like? So this is the vector U, or V transformed. Are minus 4 and 2 the coordinates of the new vector? Let us see in the figure. So the new vector was this big red guy. Its X coordinate was minus 4 and Y coordinate was 2. So the coordinate of this tip is defined by minus 4, 2, right? And that is exactly what we have got here, minus 4 and 2. So this shows very intuitively that if we are performing a linear combination, to know where a vector V will transform and what it will become, all we need to know is first see what will happen to I, then see what will happen to J. And if the original vector V was defined by a certain scaling and linear combination of I and J, all we need to do is perform the same scaling plus linear combination of the transformed I and transformed J. So all we need to keep track of is what happens to I and what happens to J. That's all. We don't need to know anything else. So I just want to show you that over here. But before that, let's just formally write it down. If we know where I and j lands right after the transformation, then we will know where any vector v lands after transformation. So if I and j gets rotated by 90 degree, just that, if that is the only thing that happens to the basis vectors I and j, then we can know that any vector v will also undergo this exact same transformation. And if I and j becomes I1 and j1, then all we need to do is keep track of that transformation, see what happens to I and j, and just apply the same scaling factor, whatever I and j originally had, to the transformed I and transformed j. So basically, any linear transformation applied on v that can change the vector v in such that it will be a linear combination of transformed I and transformed j, and the scaling factor will remain the same. So transformed I will be multiplied by 1. The original I was multiplied by 1. Transformed j will be multiplied by 2. Original j was multiplied by 2. This is a fairly interesting idea. It is simple, but I don't think many people think of linear transformations in this way. Most people think of it as a complex operation that you have to apply on any given random vector, but you don't have to think of it like that. You can think of it as transformation of basis vectors. Now let's generalize this. Just take a general vector v equal to xi plus yj, which can be written like this, right? X is the in vector format we write like this, but if we had written it like x comma y, then this is not vector. This is describing the xy coordinates of the tip of the vector, which is the same thing as which is essentially the same thing as this, but this is the vector notation, this column with the square bracket. This is the coordinates, is coordinate notation. So now let's imagine that there is a transformation that changes I to 0, 2 and j to minus 2, 0. So here when I say I and j, what I mean is this. So this I becomes this guy and this j becomes this guy. Now, can we say what happens to vector v? It's fairly simple, because the new I1 is, or I transformed, is 0, 2, and the j transformed is minus 2, 0. So what will be v transformed, or we were calling this as u? This will be nothing but x times the transformed I, right? X times I transformed plus y times j transform, because x and y were the scaling factors for I and j previously. That will remain the same. So this will be x times 0, 2, because this is the transformation of I, plus y times minus 2, 0. And this can be written in proper way as 0 times x plus minus 2 times y. And this will be 2 times x plus 0 times y. I'm keeping the 0 there to show you a point, but I mean, I can simplify this also. This will be minus 2y over here and 2x. So this is the transformation. So here, but let's not focus on this part. Let us stop it until this point. Here, what we did is, to calculate the transformation, we simply use the same scaling factor. By knowing, we simply use the same scaling factor on the transformed I and transformed j vectors. Now let's have a look at this particular guy. So the transformed vector is the same linear combination, same scalar plus linear combination of the transformed I and j, right? And this one, do you see what this is actually? This is actually a vector, a matrix multiplication. This is where linear combination relates with matrix multiplication. So here, the same thing, the same sum that we have written here can be written as first a 2 by 2 matrix, 0, minus 2, 2, 0, and then that multiplied by x and y. So here, if you expand this, you can clearly see that the expansion of this is 0 multiplied by x, 0 multiplied by x, plus minus 2 multiplied by y, plus minus 2 multiplied by y. That's the first row. Second row is 2 multiplied by x, 2 multiplied by x plus 0 multiplied by y plus 0 multiplied by y. So this is same as this. So now I hope you understand that this is how linear combination is directly related to matrix multiplication. But there is one more thing I want you to note here. The columns of this matrix, this is called as the transformation matrix, by the way. The columns of this matrix, just focus on that. The first column, which is 0, 2, is same as the transformed vector. So I had transformed into 0, 2. Originally, the I was 1, 0, right? This is what I is usually, the original basis vector of I is 1, 0. J is 0, 1. So I got transformed to 0, 2 and J got transformed to minus 2, 0. Now look at the columns here. The first column is 0, 2. Second column is minus 2, 0. So if you have a linear transformation where if the matrix, the linear transformation matrix is defined as A, B, C, D, right? Then we already know where the unit vector I is going to end up. So I will transform to be AC because this is the first column of this transformation matrix, and J will transform to be BD because this is the second column of the transformation matrix. So we already know where I and J are going to end up. So now if we are applying this transformation matrix or this transformation over any random vector xy, we can easily calculate without doing any matrix multiplication. We can calculate where the xy vector is going to be transformed to. Where is it transformed to? Basically, xy is nothing but x times I plus y times j. And so x and y are the scaling factors. But we know that I get transformed to AC, j get transformed to BD. So the after transformation, the x and y will become x times AC plus y times BD. And this is nothing but x times A plus y times B, x times C plus y times D. So this is just 2 rows. What if we had done a direct matrix multiplication A, B, C, D, A, B, C, D? This matrix, what if we had directly multiplied with the original vector? This is nothing but A times X plus B times Y, A times X plus B times Y, C times X plus D times Y, C times X plus D times Y. Isn't this the same as this? So a direct matrix multiplication, multiplying a matrix and a vector, leads to a transformation of the vector, but it's not giving you any physical intuition just to do this mathematical multiplication. All the physical intuition actually lies in the fact that A and C, this guy, forms the transformed vector of I, and BD forms the transformed vector of J, and we are basically scaling the vector, the transformed vector I, by a factor of x. We are scaling the transformed vector of J, which is BD, by a factor of y, and then we are adding those two. So that is what we did here in these 2 steps. We scaled the transformed vector of transform vector of I by a factor of x. We scaled the transform vector of J by a factor of y. Then we added them together, linear combination, and that resulted in this. So this has all the geometric or physical intuition behind how linear transformation is related to matrix multiplication. So whenever you see a matrix multiplication like this, just imagine that to be a linear transformation happening in a 2D space. So that is what I have also written here, but I don't want to take you through that because I already explained you this. So A, B, C, D, if you see a matrix like this, it's simply a linear transformation where the original I vector lands here, original J vector lands here, and then X will scale the new I vector and Y will scale the new J vector. It's very beautiful actually. Now, in the last part of today's lecture, let us practice some linear transformations so that you can appreciate how linear transformation can be very easily written in matrix format if you just simply keep track of what happens to I and J. So let's say someone asked you to write a matrix, 2 by 2 matrix that defines the linear transformation of a 90-degree counterclockwise rotation transformation. If you were directly writing this matrix, it is a bit hard to think about, like this ABCD, what are the values of ABCD? It's a little bit difficult to think about. But if you think of this matrix, this transformation or matrix multiplication in terms of what happens to I and J, it's much more easy to think about. So we are just doing 90-degree counterclockwise rotation, right? So what happens to I, or let's say what happens to J first? J will rotate over here, right? So this is the new J, and I'm sorry, I cannot position it exactly on top of this. And the new I is this. So the transformation is nothing but the new I became 0, 1. The new J became -1, 0. So this first column is where I lands. Second column is where J lands. I landed at the coordinates where the tip of the I landed after rotation was 0, 1. So that is this 0, 1. The tip, the coordinates where the tip of the J landed is -1, 0. That is this -1, 0. So now this is the transformation vector. So you don't have to believe when we say this is the transformation vector that does the 90-degree rotation counterclockwise. We can apply it directly on top of any vector. So let's take this vector V. So this vector V is nothing but 1, 1, right? So that is what this vector is defined as. And we know that when 90-degree rotation is performed, this vector should be like this, and this should be -1. The x coordinate is -1, y is 1. So this is what the vector should get transformed to. Now let's see if this matrix multiplication performed on top of this vector will indeed result in this. So 0, -1, actually I can multiply here. This multiplied by 1, 1 equal to 0 times 1 plus -1 times 1, which is -1. 1 times 1 plus 0 times 1, which is 1. So this became -1, 1. So 1, 1 got transformed into -1, 1. Isn't that what minus 90-degree, like 90-degree counterclockwise rotation also doing? Same thing. So this is how we can easily define linear transformations in terms of matrices if we simply keep track of what happens to the basis vector I and basis vector J. Now let us define a shear transformation. So what happens in shear? In shear, it's not just rotation, right? It's like something is being elongated and something is being squished. So let's say a shear transformation is such that things are getting a bit elongated along the 45-degree direction. So or rather maybe I can define it such that, so usually this is a shear, right? If we have an object like this, the base will remain wherever it is, and a push will be applied, and then the object will transform to something like this. So this is what is shear. So what I can do here is to define the shear transformation. I will keep it here itself. I will not move it. I'll simply move J, and let's say the shear is happening by a 45-degree angle. So now we want to know how to represent this shear operation by a matrix. So let us pick this vector. So if we are doing a 45-degree operation, this will be here, right? This unit vector will be like this. So actually, maybe I should keep the height like this. Okay. So what happened is now the I remained the same. So I was transformed into same whatever it was originally, 1, 0. But the J became transformed into 1, 1. And now what is the matrix that defines the operation? Wherever I lands will be the first column. Wherever J lands will be the second column. So now let's see what happens to a particular vector under this shear operation. Because now if I say that this is a shear operation, this is a matrix that represents the shear operation, you have to believe me, but you don't have to believe. We can just apply it on top of a vector to see what actually happens to the vector. So let's say the vector is this, maybe this guy. So shear should do something to this vector, right? So this vector is nothing but 0, 2. So what happens to 0, 2 if this shear is applied? Then what happens is 1 times 0 plus 1 times 2, so that will be 2. 0 times 0 plus 1 times 2, that will be 2. So the vector 0, 2 got transformed to 2, 2, which is 0, 2 was this, 2, 2 is this. So the vector, and in shear also that's what happens, right? So this part will become something like this. So here this vector became something like this. So this is the shear operation. So if you were asked to write a shear operation matrix directly without thinking about I and j, it will be much more difficult. But if you think of shear in terms of what happens to the basis vector I and basis vector j, it's much more easy to visualize. So this is again a linear transformation. Now let's do one last, probably the most interesting linear transformations, and then we can conclude the lecture. So let us perform a particular transformation that squishes both vectors into one single parallel line. So what I mean by that is, after transformation, the vector transformed vector I and transformed vector j should fall on the same line. And you will also see why this is a fascinating example with just one minor thing that I will note before I conclude the lecture. So how can I and j after transformation stay on one parallel line? Maybe I can be like this, right? And maybe j can be like this. So let's say after transformation, I becomes 1, 1, right? That's what happened to I over here. And j becomes minus 1, minus 1. So in this particular example, the vectors are transformed in such a way that I and j are parallel or anti-parallel. I mean, they are along the same line. So now what is the transformation matrix in this case? 1, 1, minus 1, minus 1, because the first column will be same as the transformed I. Second column will be same as the transformed j. So now this is the transformation vector. So now let's see what happens to any random vector in the xy plane. So maybe in the xy plane, I select a random vector like this. What is this? Maybe minus 1, and 3, right? This is roughly minus 1 and 3. What happens to this vector? Let's see. So minus 1, 3. This should ideally, so what did we do? We did the transformation such that squishing happens. All the vectors is getting squished into one single line. So ideally, this vector should also get transformed and squished into this line. Let's see if that is indeed happening or not. So this is minus 1 times minus 1, which is minus 1, plus minus 3, which is minus 4. Then 1 times minus 1, which is minus 1, plus minus 3. This is also minus 4. So this vector, which was like this, it became something like this, minus 4, minus 4. So the vector got transformed into this line. And this applies to any vector. So if we take this vector, which is, let's say, 5, 0, this also will get transformed such that it will stay along this line. So 1, minus 1, 1, minus 1. This is the transformation vector. 1, minus 1. And the vector we are transforming is 5, 0. And this will become 1 times 5 plus minus 1 times 0, which is 5. 1 times 5 plus minus 1 times 0, this is also 5. So this guy, this 5, 0 vector got transformed into this vector, which is along again the same straight line. So here there is one interesting property that I want you to note. So in such a transformation, now the transformed basis vector, so the original basis vector I and j could span the entire xy space, right? So using I and j, we could construct any vector in the xy space. However, with the transformed I and j vectors, because the transformed I was 1, 1 and transformed j was minus 1, minus 1, these two vectors are not linearly independent because they are parallel to each other. So if you multiply this guy by minus 1, you get the transform. If you multiply transformed I by minus 1, you get the transformed j. If you multiply transformed j with minus 1, you get the transformed I. So the transformed I and transformed j are not linearly independent. So, and because of that, the transformed I and transformed j cannot span the entire 2D space. It can only span this one single one-dimensional line. So that because of the way it got transformed. So this also, you can see that if you look at the determinant of this transformation matrix, 1 times minus 1 minus 1 times minus 1. So it is minus 1 minus minus 1. It is 0. So the determinant of this matrix would be 0 in such cases. I don't want to go into the details of determinant and how it relates to a linear transformation in this lecture, but I just wanted you to just briefly observe for it very in this very simple example. But I want to end this lecture at this point. But let us just recap what we studied in this lecture. We understood that a linear transformation means it has to follow two properties. One is all points that were originally on a line should remain on a line after linear transformation, right? So that's what we saw in this example. In this example, the points that remained on a line again remained on a line after transformation. The second property was the origin has to be fixed. Origin should not move. So we saw that this was not a linear transformation, this case 3, because origin was moving. Now, we also saw that we can represent the linear transformation such that if V is a vector that is defined by the scaling plus linear combination of I and j, then the transformed V after transformation, we can define it by the scaling and linear combination of transformed I and transformed j. And the scaling factor remains the same. So if the original vector V was defined by 3 times I plus 5 times j, then the new vector V after transformation will be defined by 3 times the transformed I plus 5 times transformed j. So we saw that, and we directly saw this with a specific example. Then we saw that any general vector, if it is undergoing a transformation, especially in this 2D case, the transformation itself can be described by a 2 by 2 matrix. And the 2 by 2 matrix is in such a way that the first column of this 2 by 2 matrix describes where the vector I ends up, and the second column of the 2 by 2 matrix, this guy, describes where the vector j ends up after transformation. So it was much more intuitive now to think of matrix multiplication as linear transformation, because a matrix multiplication of this will result in something, but the same thing can be described as x times 0, 2 plus y times minus 2, 0. So a linear matrix is probably a way to represent linear combination rather than vice versa, because here we are not trying to say that, hey, look, matrix multiplication has a very intuitive way to understand it. No, that's not the way. You should think the opposite way. Linear combinations can be described by transformations of I and j vectors, and then you scaling them and linearly adding them. And the way this can be easily represented mathematically is in the form of a matrix multiplication. So think of matrix multiplication like that. And then finally, we also looked at some specific examples, right? We practiced some linear transformations. So if it's a counterclockwise 90-degree rotation, we just need to keep track of what happens to I and j. And wherever I and j ends up, you write wherever I ends up as the first column, j ends up as the second column. And then if you apply this on any given vector by multiplying the matrix with the vector, you get a resultant vector. And this resultant vector is indeed the transformed vector. We saw that with this example. A shear transformation also we defined simply by keeping track of what happens to I and j. So here I remained fixed, j became something like this. So j was originally here and it became along this 45-degree line. And this gave us the matrix that represents the shear transformation. And when this transformation is applied to any given vector, that vector also undergoes the shear operation. And finally, we saw squishing operation, where all vectors in the 2D plane are squished into one single parallel line. And there is a surprising property over here based on the determinant. The determinant of the transformation matrix is 0. But we'll be describing more of that in the next lecture. In this lecture, I just want you to take away this basic geometric intuition behind linear transformation, also known as matrix multiplication. So with that, let us conclude this lecture. Thank you so much. And thank you for attending this lecture. I'll see you again in the next one. Until then, take care, please. Bye.